Okay. Beleza. Good morning. We start today just like we started yesterday with a lecture from Dan. The first 7 or 8 minutes is done on the blackboard, and then he comes to discuss some atomic physics topics like matter interaction and this kind of topic. So.
Let's continue. Just to remind you where we left off last time, I'd been talking about the motion of a spin in a magnetic field and the transitions induced by a rotating field, the so-called Rabi resonance formula. Let me just go back to it for a second. Recall that we're interested in a case in the laboratory. We have a static field like this. We have a rotating field like this. And if we go into a rotating frame going along with this field over here, then the effect is to reduce the static field by an amount omega over gamma, where the magnetic moment of this particle we've written as the gyromagnetic ratio times the angular momentum gamma times h bar times I. Yeah. And so the system then evolves around this static field in this rotating system. So if the magnetic moment initially is pointing in this direction over here, here we have mu at t equals 0, then later on it goes around like that. And I left it as a construction to show that the z component of this at some time later t was given by 1 minus twice omega. Well, I've used both large and small r's here, omega r squared over omega. You want small? It's r plus omega minus omega naught squared times the sine squared of 1/2 omega r squared plus omega minus omega naught squared. This is in your notes. It'll be in the notes that I've given out, so there's no need to copy. But I would like to interpret this slightly differently. If we have a spin 1/2 system, then the z component of mu can be written as gamma times h bar times the z component of I, which will be m sub I, where m sub I is equal to plus or minus 1/2. And the expectation value of mu z then is just going to be equal to 1/2 gamma h bar times the probability that it's in the state p 1/2 minus the probability that it's in the state of p minus 1/2, p 1/2 and p minus 1/2. Yeah. So these are the probabilities, and of course the sum of the probabilities, p 1/2 plus p minus 1/2 is equal to 1. So I can write this just as well as 1/2 gamma times h bar times 1 minus twice the probability of being in the minus 1/2 state. So we see that the probability of being in the minus 1/2 state after time t over here, just by comparing this formula over here with this formula here, particularly if I put in the magnetic moment in front of it, which is gamma times h bar. The probability of being in the minus 1/2 state is given by this formula over here. The probability, maybe a better way of putting it, the probability that it's gone from 1/2 to the -1/2, because it started in the +1/2. So this is what we call the probability of a transition. The transition 1/2 to -1/2 is given by, again, this now familiar formula, which is omega Rabi squared over omega Rabi squared plus omega minus omega naught squared times this sine squared of 1/2. Omega Rabi squared plus omega minus omega naught squared times t. Okay. Let's look at what happens when the system starts out. Okay. Small t. What does small t mean? Well, it means that the argument of this thing over here is going to be rather small. It means you can replace the sign of the thing with its, with its value. In that case, the probability of -1/2 is approximately equal to 1/4 omega Rabi squared times t squared. Okay. Well, let's look at the rate of transition if we want. The rate of change of the transition is the rate of change of its being in this new state. So the transition rate I'll put this in quotation marks, which is dp by dt, is going to be equal to 1/2 omega Rabi squared t. And the question is, why should the system behave like that? One knows that if you have a system and you apply radiation, it starts making transitions. If I look at the population, say, of the +1/2 state as a function of time, according to this is, here we have the n in the plus state as a function of time. Say it starts off at n0 over here. What we're going to see over here is that it is oscillating back and forth like that. Whereas normally you'd expect that dn by dt is equal to minus some rate times n. This is a normal decay curve. You'd expect it to behave like this. So it not only starts out entirely differently, it's moving down quadratically. This rate over here, this is a constant. Of course, this is not a constant rate there. It's oscillating, which is an unnatural way to behave. It does do this. You can actually, I showed, I think, a quick picture of Rabi oscillations. Under the right conditions, that these are quite manifest. And so there's nothing wrong with the Rabi formula, but there is something wrong with how we're trying to apply it over here. The Rabi resonance was designed for this the very first situation of resonance, where you have an atomic beam coming along. You can select the spin state, okay, with a magnet. Okay? And then it goes through, you do this with inhomogeneous fields, it goes through then a homogeneous field where it starts precessing, and then you do this trick. You apply the rotating field and you can turn it over, and then it goes through another magnet and you can see which field it was in. So you really are approaching this ideal situation very well, where the atom just sees a pure rotating field for a little while. That is totally different from the usual situation in radiation. In fact, the usual situation in radiation is where you're radiating the system with very broadband radiation with maybe thermal radiation. Lasers, well, the laser can be very narrow. It can also be rather broad. So this is very handy to know about for manipulating atoms, but I'd like to address the more general question right now of atoms and radiation fields, and that's what I'll be talking about today. Now, a lot of this gets into details, and I realize I don't want to bore you too much with details. They are in the notes that will be handed out, so I'm going to skip some of the details, but I would like to outline it. But what I'd like to do is to start with talking about the granddaddy radiation problem, which was the problem of blackbody radiation. Famous problem. It started really quantum theory, and the problem was to find the spectrum of radiation in a warm cavity, or any cavity. They didn't use the terms cavity. In those days, they didn't have cavities, but you had a black body. You had an oven with a hole in it, and you looked at the radiation which came out. And of course, it was in trying to fit that radiation, that observed spectrum to theory that Planck came out with his quantum hypothesis in 1900. You know, we had this famous problem. It's an interesting history. The ultraviolet catastrophe, if you calculate the density of modes in space, they're infinite. And if you're going to apply the equipartition theorem, you immediately get infinite energy. This is called the ultraviolet catastrophe. It's generally considered this is what motivated really the start of quantum mechanics or quantum physics. It's always interesting when you go back and really look at the history of these things. Planck postulated his radiation formula in 1900. The term ultraviolet catastrophe got first used in 1905 when Rayleigh was considering the problem again and pointed out the ultraviolet catastrophe. He knew about Planck's formula and said, Professor Planck has a marvelous, has a formula which gives exquisite agreement with the theory, but I can't possibly understand it. And Planck couldn't either. That Planck put forward this mathematical way, namely quantizing the energies of harmonic oscillators, and pointed out that if you do this, you get the right answer, but he didn't really believe it. It was Einstein who started it all in 1905 on his paper on the photoelectric effect, which is a marvelous paper if one looks at it. He really took the idea of the discrete nature of radiation as a starting point. His paper starts out by saying that although we know that the wave theory of light works extremely well, it's interesting to note that it has only been observed in essentially macroscopic phenomena. We have no microscopic theory of the transition of energy from the radiation field to matter. And so that we may maintain the wave theory of light, but there may be much more to it than that. And then goes on and postulates the existence of energy quanta, not at all related. He makes no reference at all really to Planck's way of doing things, which is purely artificial. It was based on looking at the entropy of the radiation field. So it was a marvelous paper, and it has a very interesting title. It's called On a Heuristic Theory of the Interaction of Radiation with Matter. Heuristic meant that he didn't, it's something you put forward which is so wild that you don't really believe it, but it's useful for motivating discussion. And he never, there's an element of doubt in that paper which he never lost. It eventually divorced him from quantum mechanics, but it was there from the very beginning. But what I would like to do is to talk about not that paper, but the famous paper on the absorption and radiation of light by matter, the 1917 paper on radiation theory, which, well, do you know about the Einstein A and B coefficients? Have many of you heard about this? Have many of you heard about it but are afraid to put your hands up? Okay. Yeah, it's normally taught, and it's quite straightforward. But if you look at the paper itself, it is much richer. And so this is sort of an historical digression, but I thought it would be interesting and worthwhile for you. So let me talk a little bit about what's really going on in Einstein's paper. And now we have to go back and do something to this. Is it coming up? Ah. Was that too fast for you? Ah. Oh, okay, there we go. This is 19 paper. It is available in translation into English, perhaps into Portuguese. Okay, it's on the quantum theory of radiation. What Einstein was really interested in was not absorption and radiation of light. What he was interested in is thermal equilibrium. And the question that he wanted to ask is, how do atoms come into thermal equilibrium with a radiation field? The Planck radiation formula was well known and well established then. But the question is, suppose you have a gas of atoms just moving around in free space, and the only thing they interact with is radiation. How does the system come into thermal equilibrium? And he looked at this system rather completely. He wanted to know how atoms come into thermal equilibrium with respect to the internal states. Remember, I talked in my first lecture about how we have achieved complete control over atoms. We can control their internal states completely, and we can now control their external, their translational states completely. Einstein was interested in that problem from the very beginning. He understood the nature of both of these forms of energy in the atoms, and that they interact with radiation rather differently. And he wanted to know how both of those systems came into thermal equilibrium. The first part, which is the part which most people know, is how the energy levels of an atom achieve equilibrium with thermal or black body radiation. But he went on to ask, how do the momentum states of the atoms come into thermal equilibrium? Namely, he took it for granted that the atoms obeyed the Maxwell-Boltzmann distribution law, which is based on classical statistical mechanics. Okay? Suppose you put a lot of atoms into the cavity and suppose they all have the same speed to begin with. Well, eventually they'll get into equilibrium with the thermal radiation and they'll obey the Maxwell-Boltzmann law. And so the question is, how do they do that? So he was interested both in energy exchange and, as it turns out, momentum exchange with the atoms. What he did was rather, well, the whole paper was rather novel, but I would not have thought of doing it this way. What he did was to assume that the atoms are in thermal equilibrium, and then find out what thermal field is needed to maintain the equilibrium. Okay? And what you find is that if the atoms are in thermal equilibrium, the radiation field has to be the Planck field. So he made a number of assumptions, and they're very interesting assumptions. The first one is that he took for granted the existence of stationary states of atoms. That idea had been postulated just a few years before by Bohr, but he just took it for granted. That's the way things are. And he considered just two levels of interest. That is the only quantum assumption that he really makes in this paper. Okay. He assumed that the level populations are governed by Boltzmann's law, that this distribution of these two states is given by Boltzmann. A rather unjustified assumption. If you're going to assume that the energy levels obey a new mechanics, why should the distribution of energies obey Boltzmann's law, which is perfectly classical? But it worked, and he did it. And then he assumed that atoms absorb energy and go from the ground state to the excited state at some rate. It's the Einstein coefficient B times the energy density rho of nu. Rho is the energy per unit volume per unit time, assuming that it's isotropic. This assumption is really quite reasonable. If you look at a classical oscillator and you drive it by random fluctuating fields in all direction, you'll find that it exchanges energy with the fields according to the energy density that's present. Okay. Well, what were the conclusions of the first part? The first is that the atoms could absorb energy from the field. Let's see, did I leave out a paper here? Yeah, okay. The atoms emit energy at the same rate they absorb energy. If you have an oscillator in a field, depending on the instantaneous phase of the oscillator with respect to the field, it'll either absorb energy or it'll emit energy. So the fact that the absorption and the emission processes come together is perfectly classical. Then spontaneous emission. He pointed out that this process had to exist. I don't know who talked about it before then except Michelson in 1885, who made studies of the width of spectral lines. These are fascinating studies. When he had his interferometer, he could measure line widths, and he made a very detailed measurements on line widths and learned all sorts of physics from it. He learned about Doppler broadening of the lines, and from that checked Maxwell's Boltzmann's law. He also learned about collisional broadening of the line, and that information was directly used by Lorentz. But he pointed out that even if you don't have a collisional broadening or you don't have motional broadening, that the line would still have some width to it because all oscillators decay, and if they decay, they're going to have some sort of natural line width. So that's the first place I think that the idea of the natural line width, which is part of spontaneous emission, came up. Einstein simply said that you had to have this process. It's very simple also to see why you have to have that process. Suppose you have a lot of excited atoms in empty space at absolute zero. Well, thermal equilibrium means all the atoms are in the ground state. Right? How do they get there? They have to just do it. So he postulated that you had to have this spontaneous emission process. And it was a real problem for him, as I will explain. Well, the conclusions of Part A, it's gone through in the notes, it's really quite simple. But the important conclusions are that spontaneous emission is essential. The absorption frequency of these atoms has to obey the Bohr frequency relation. He didn't assume the Bohr frequency relation. He showed that this had to follow from that. And he also showed that the stimulated emission rate is proportional to the spontaneous emission rate. So those are the major findings of the first part of this. He also showed, though, what he really set out to find out was that the radiation field had to be given by the Planck formula. He commented, I deduced in a remarkably simple and general manner form Planck's, well, that's meant to be a formula, yeah. Spontaneous emission, he introduced in a very cavalier fashion. He said the atoms will radiate spontaneously at a uniform rate in analogy with the law of radioactive decay. Radioactive decay had been discovered around the turn of the century, and it caused a great deal of perplexity. People did not know why things should decay spontaneously. It's against sort of all classical ideas that things could happen randomly like that. So it was an intellectual problem then. It was a real intellectual problem for Einstein, but he did not face it right here. He just took it as an analogy. But he makes this comment at the end of the section. The weakness of the theory lies in the fact that it leaves moment and direction of the elementary process to chance, that is spontaneous emission. All the same, I have complete confidence in the reliability of the method. So he's saying there's a conceptual flaw in the method. Nonetheless, he thinks the method is correct. Now, on the analogy of spontaneous emission and radioactive decay, this was found around 1900, and it really caused people a lot of agonizing. There's an interesting quote by Abraham Peiss, who's really the greatest historian of that period, about James Jeans. Interesting but difficult questions arise when we this is what James Jeans said 50 years, not 50 years, 20, 30 years later. Interesting but difficult questions arise when we discuss which atoms will disintegrate first and which will live longest without disintegration. Suppose that 500 million atoms are due to disintegrate in the next second. What we may inquire determines which particular atoms will fill the quota. It seemed to remove causality from the large part of our picture of the physical world. Okay? Well, this problem really bothered Einstein. It bothered him when he first introduced his ideas in 1905. Labeling the theory heuristic meant he had deep reservations about it. And of course, his unwillingness to accept probabilistic descriptions of nature eventually divorced him from quantum mechanics. So many people think this is one of the great tragedies of the 20th century, that Einstein could not reconcile himself to that. But the misgivings were there from the very beginning. Nonetheless, at least in 1917, he was willing to live with them. Okay. Part B, how the external states, the momentum states of a gas of atoms achieve equilibrium with thermal radiation. And this is the part most people don't look, but it's really very ingenious. He assumes the atoms exchange, they absorb and radiate, not only energy, but also momentum with the thermal radiation field, by stimulated and spontaneous emission. And these processes generate a viscous retarding force. This viscous retarding force is essentially the force of optical molasses, which is used in laser cooling. He assumes that the atom's velocity distribution obeys the Maxwell-Boltzmann law for velocities in a gas. And what he points out that whenever an atom absorbs a photon, its momentum is changed, so that the radiation, the spectrum it sees then, has been altered. It's not the spectrum it saw when it was absorbing it. So absorbing and emitting radiation continually changes the spectrum the atom sees. But the result of these effects is to cause a spread in the velocities of the atoms. And that spread depends on the shape of the spectrum. Then he proves, though, for the velocity spread to be given by the Maxwell-Boltzmann law, the radiation field must be described by the Planck law. What's the significance? Well, general significance is that the basic radiation processes, spontaneous and stimulated emission, were elucidated for the first time, and their fundamental relations were revealed. The fundamental nature of spontaneous emission was established. The Planck radiation law was rederived by totally new arguments. More importantly, the full nature of radiative quanta, that is, photons, was elucidated for the first time. People kind of knew about this before, but it was Einstein who really sort of made the photon idea really concrete in this paper. Incidentally, he did not use the term photon. He always talked about elementary excitations. He did not like the term photon. But this is the paper really where the photon was, for all practical purposes, made legitimate. Now, his arguments for the interactions of atoms with the field pointed out that for the atoms to have their Maxwell-Boltzmann distribution, the field has to be the Planck field. If one assumes that the atom distribution was essentially monochromatic, you would end up, by these arguments, showing that the radiation field had to be essentially monochromatic. what he's done here is lay the intellectual foundations for laser cooling, because in fact, with laser cooling, the velocity distribution of the atoms approaches as monochromatic as the field can be, namely the spectrum always has a width, which is due to the Doppler broadening of it. So if one assumes that the atoms were initially all moving with, say, at zero temperature, if you like, but that the radiation field that they interacted with was given by the natural line width of the atoms, you'd end up with a Doppler limit. It's often been pointed out that in this paper, really Einstein, well, he almost invented the laser, pointing out the importance of stimulated emission. Well, this paper almost invented atom cooling. And as an interesting footnote to this, people didn't really, like most of his papers, many of his papers, didn't take it too seriously at the time. But the experimental verification of the particle-like properties of the photon were proved decisively in 1923 by the Compton effect. Remember, in the Compton effect that you have an electron which is coming in, a quanta which comes in and scatters off an electron and gives momentum to the electron and goes off in a different direction, and because it is given off momentum, it's given off energy and its frequency changes. That's the Compton effect. Discovered in 1923. Compton got the Nobel Prize for that. An interesting footnote to that paper is if you read the paper, somehow or other Compton manages to overlook talking about Einstein altogether. He just doesn't mention Einstein. He just assumes that the photon has this momentum. This is a rather new idea, and it was Einstein's idea, but apparently he felt justified in sort of taking it for granted at the time. So maybe this is a good point to stop.
Thank you. Well, yesterday we had Dam reflecting on atomic physics. Today we had done teaching. Tomorrow we have done on an interview about Bose-Einstein condensation and his trajectory. But now we change to a live talk from our friend from Italy, Massimo. Massimo, do you hear us?
Yes, I'm here.
Great. So thank you, Massimo, for accepting our invitation to talk today. Massimo is, I think, one of the most prominent physicists in Italy. And we talk about today about quantum mechanics, what they do at LENS in Florence, and some of his time with Dan Kleppner also. Massimo, thank you. I think you don't see us here, but we hear you, and if you need feedback, just ask, and you hear us just like this. Thank you.
Okay. Good morning. So what you see now? You see the first slides of the talk?
We see you full screen, and we will change to presentation plus you.
Yes, let me say that, of course, it is a pleasure, a human pleasure, to say something at this conference, because the link between Brazilian science and myself and Italy is lasting since too many decades, and also this idea of celebrating the 100 years of quantum mechanics, giving a tribute to Dan Kleppner, is also another, very important motivation for staying here, with you. My presentation will be a little bit a mixed presentation between some historical experimental results, even interaction with Dan Kleppner, and also some contemporary physics that we are doing in Florence at Lens Laboratory, where Dan loved very much towns like Florence, I mean, full of a culture. And also I want to show some new things that we are doing or planning, which maybe can be interesting for colleagues from Brazil. I mean, we have several times we have colleagues from Brazil working with us. Let me start. So this talk will deal about atomic physics, essentially, getting inspiration on what we do in atomic physics at Lens, but also will be a little bit an history, I mean, of atomic physics. So these were the late 80s in Pisa. We are in front of the Scuola Normale in Pisa. Well, we organized with the colleague Bassani from the Scuola Normale and with Ted Hensch a conference on the most fundamental atom, the hydrogen atom. Because, as you know, studying hydrogen allow you to discover new physics and fundamental aspect of science. There, we had a lecture by Dan, and this was about the trapped atomic hydrogen. You know that Dan spent a long time of his activity in trapping atomic hydrogen and also doing laser spectroscopy of the atomic hydrogen. And I just listened to the last part of the lecture of this morning of Dan, and I understand that tomorrow the lecture will be, I think, devoted to the BEC. And so when the BEC happened, rather soon, later the discovery, we organized in Italy, in Varenna, on Lake Como, practically the first important school summarizing all the state of art on the field. And we were glad, very glad, I was personally very glad that Dan could be among the speakers in that school. I mean, people, the rare people who had a Bose-Einstein condensate at that time, because after the spectroscopy of hydrogen, trapped hydrogen, as you know, Dan developed a long effort to achieve the Bose-Einstein condensation in hydrogen, because the idea of the thinking was that the easiest atoms in which to observe the Bose-Einstein condensation should have been hydrogen because of the smallest mass. Well, it was not like this, but we were glad that after so many efforts, Dan was in time to report his Bose-Einstein condensate of hydrogen in the Varenna school. And that school was a little bit a triumph of, atomic physics. Here in blue, I have listed all the Nobel Prizes who won the Nobel Prize mostly after that school. So Dan and we all were in a very, very good, company. And this is the paper that Dan published with his group in about Bose-Einstein condensation of atomic hydrogen. I must say that the story of trapping hydrogen, cooling, and things like this was a very, energy demanding project, which eventually also produced a lot of excellent physics. So let's see what's happened at length. So we started now with hydrogen, but then you have to think to easy atoms like rubidium, of course, which was the first Bose-Einstein condensate. This is a group of very, very young people with whom we put together the experiment to try to achieve, the Bose-Einstein condensate. Cataliotti, Tino, Prevedelli, Fort, Marin. I mean, many of them. And we started achieving actually the Bose-Einstein condensation. And the field which was started in science with the atoms was essentially the field of on the possibility of simulating other physics using atoms and light. I want to show this experiment that we did on creating an array of Bose-Einstein condensate, which were superfluid, separated by the by regular barrier of light. So this was an array that we could control, and I have chosen this because you see the oscillation of this coherent linked Bose-Einstein condensate respect the theory. You see that the frequency of oscillation follows the prediction of the theory according to the height of the barrier. But I want to show this example to start with the simulation, simply telling you that this oscillation works like I've shown regularly until a certain level. I mean, when we go very faster than a certain limit, then there is a dynamical instability, which is triggered by a nonlinearity. So essentially, we have the breakdown over superfluidity, and the system becomes, unstable and chaotic. And one of the times I visited Dan at MIT, and this was on my way to give a lecture in Italy on Lagrange. Lagrange is, the one of analytical, mechanics, and one of the first exercises that you find in the Lev Landau book on analytical mechanics, practically copying or inspiring by Lagrange, is essentially on the composite pendulum. And then Dan made for me a lecture that I show you.
Lend itself to description by Lagrangian mechanics quite well. There would be two generalized coordinates, this angle here and this angle there. And with it, you could predict the motion, which is really very nice. Like that.
So you see our condensate is regular oscillation where the amplitude is small, but if you increase...
An anti-symmetric mode. And all this we can tell from Lagrangian mechanics. So we can write the equations of motion. But what is a little bit unexpected is that if you start with a given energy, for instance, this amount of potential energy, the system can behave like that. But it can also behave like this. This is chaotic motion. You can write the equations of motion with Lagrangian mechanics, but you can't solve them. Want to look at this very carefully because it'll never, never, never do exactly this again. There's no way to predict this. A good way to determine whether or not the motion is chaotic is that if it's regular, like this, you can grab it. But if it's chaotic, like that, you will really do yourself an injury if you try to grab it. So this is a model that I made when I was studying to create the relationship of quantum mechanics to chaos. And this is a good example of classical chaos. The end.
So you can get any kind of dynamics with these oscillations. And so with the BC, we could study, these things, but this is attribute also to Dan, who created this spatial pendulum, double pendulum, to essentially teach. So he repeated for me one of his lectures to the students of MIT. So this is another important characteristic of Dan, that he really was a professor. I mean, an extraordinary teacher who created, in this case, this artifact to show the instabilities, dynamical or not, the chaos, which can happen in a double pendulum, simply depending on the initial condition. But during the time, starting with rubidium, in the laboratory in Florence, we also participated to the broad development of the BEC, which at the beginning was simply a mystery, some mystery that could only happen with rubidium and with taking care of too many details. And instead, we enlarged the field to potassium with a very interesting method. I mean, mixing potassium and rubidium and using the cooling down of rubidium to cool also potassium. And so to have, for instance, a Bose mixture when we were using the bosonic, one of the bosonic isotopes of potassium, but also we were able to create a degeneracy, a Fermi degeneracy, using potassium 40, which is a fermion, and potassium 40 was brought to degeneration in also with sympathetic cooling with rubidium. Here, there is a piece of history, because this was done in 2002 in Arcetri, where lens was placed at the beginning of the activity, exactly 100 meters from where Enrico Fermi in 1926 had predicted the Fermi statistics, what happened so to the Fermi degeneracy, the degeneracy of a monatomic atom brought to very low, temperatures. So the place was that. This is the paper on the quantization of a perfect monatomic gas, which gave origin to the Fermi statistics, and several years later, something like 78 years later, we were able to have this degeneracy. And just to inform all of you, we are going to have celebrations of this Fermi anniversary, both in Rome and in in Florence. But and these are the people young those time. You maybe recognize Giovanni Modugno sitting, and Giacomo Roati, who you know very well because he likes to come in your laboratory, and you have developed together very beautiful science. This production of a Fermi gas of atoms was very much interesting because, in particular, we were the first in placing a degenerate Fermi gas in an optical lattice, essentially creating the first tool for what became, the quantum simulation with fermions in optical lattices. But the second bosonic isotope of potassium, which is potassium-39, has the characteristic of having a strong Feshbach resonance, which means that if you add a magnetic field, the proper value, you can tune the interaction from attractive to repulsive, and then also to no interaction. With this system, we were then able to study for instance, the Anderson localization. But this Feshbach mechanism, in order to really learn how it works, I decided to show potassium-39, because to understand this mechanism, you can go to one of the several fantastic papers that Dan wrote on physics today, describing different kind of physics. This is the one that he wrote on Professor Feshbach and his resonance. Now, the Professor Feshbach resonance has opened many important possibilities, either going to zero interaction and maybe doing the Anderson localization, but especially in the new location of lens, which is in a more modern laboratory, we could develop much new physics, and in particular, if you go to the lithium, this is under Giacomo Roati. Lithium has also the characteristic of having a resonance in a Feshbach resonance, and then you can go from a fermionic gas to a Bose-Einstein condensate or coupled fermions to a Fermi superfluid. I will show you. So again, this is the power of different atoms with different characteristics, but also with a the possibility of the flashback resonance. And here the list is long. I will just describe something of this issue. In particular, I would like to start from the lithium, laboratory, where you have the possibility of creating a Fermi superfluid to couple two fermions like in a Cooper pair, and then you can also mimic you can also mimic what's happened in a solid, for instance, in the superconductors, considering that the analogies and the difference, the difference in mass, of course, the lattice constants is different. You can tune the barrier, so the tunneling rate. You can change, the interaction, and so on. So you can do a lot of interesting physics also, because with the sophisticated tools like the possibility of creating a focus of light on the atoms, but also using digital micro mirror device, you can tailor the situation. For instance, of course, the Giacomo Rovati friends are happy to show the skyline of Florence made by lithium superfluid, but you can also do important new physics, because you can add to the fermionic superfluid, you can add a slice of light, and then you can study the tunneling between one side and the other, and also gently changing the intensity and the thickness of the light shade. You can tune the characteristics. So essentially, you can reobserve with precision the physics. Here, in this case, also with in situ imaging of fermioni going one side or to the other, with a number of particle unbalance, which will allow exactly this change of chemical potential and then going up and down. You can go through the literature, because, for instance, you can change the barrier. You can create an oscillation, in the barrier, reproducing what was happening in the ordinary Josephson superconducting, Josephson effects, which are very interesting, like the Shapiro. You can reproduce a situation that is done in, if you want, in solid state physics, which here you see the steps by step by these Shapiro steps, and a comparison with what happened in the ordinary superconducting junction. This seemed just a curiosity, I think, even though important, because you see these are papers published, for instance, this one in Science, but immediately it became very, very important again, because you can now with light shape the this superconducting, material in a regular box. And so you can create arrays of Josephson junctions, a little bit like we have done at the beginning of this talk with the many Josephson junctions put together, oscillating in 1D in an optical lattice. But here you can essentially have a multiplexed atomic Josephson junction. And so you can do parallel circuits, which now becomes, again, very much important with they are more advertised because of the Nobel Prize, which has been given this year essentially to this macroscopic effect with the superconducting junction, which are also used or could be used for as bits for quantum computation. I'm telling this because you will see later I will a little bit address these kind of questions. So essentially, with light and ultra cold atoms, superfluid fermionic atoms, this is really an interesting field. This is the group of young people. But going from hydrogen to rubidium, to potassium, lithium, we were essentially linked to alkali atoms, so atoms with just one electron. So I would say 15 years ago, we started with a new atom, ytterbium, which has the characteristic of having two electrons in, and so the ground state is with 0, like the helium, no? Is to have a 0 angular momentum. And instead, the spin for this atom can only come from the nucleus. For instance, in this isotope 163, which 73, which is a fermion also, you can play with 6 different spin possible states, and you can go from one spin to the other using Raman excitation with the 2 photons from a laser. And this allows you to mimic another kind of a little bit high energy physics, because you can do now simulation of symmetries, in high symmetries in nature, or you can create artificial magnetic fields and even adding an artificial dimension, this tunneling between the spins, which has to be added to the real tunneling in the optical lattices, and then you can study, phenomena, for instance, like the Hall effect, because you can have this artificial magnetic field, you can have a sort of current tunneling going all around the synthetic dimension, the real dimension. And then if with lithium we were simulating Josephson junction, here we can simulate all effects. This is essentially the lab of Leonardo Fallani, and which now I want to tell, making some other consideration later. A very interesting atom which entered in the lab was thanks to Giovanni Modugno with an atom, dysprosium, which has the characteristic of having strong dipolar ground state. So you have an interaction long state. I mean, so you can have a superfluid, but then in addition to the superfluid, you have essentially a periodic structure. So you can create essentially what is called a superfluid, a super solid, which was longly predicted by a theoretician. And you can, this is something totally new, was something totally new when it was discovered. And here is a very interesting effect that having now a super solid, which means a super fluid, but in presence of a sort a periodic structure. Now, if you go back to the Josephson junction that I show with my first slide, here you can have a Josephson oscillation. You see there on in the left part of the figure. You can have Josephson oscillation of the superfluid part across the if you want the super solid, so the solid, the periodic structure of solid state. So it's all homemade. I mean, you don't need to add, to add light. This is simply the consequence of the dipolar strong, interaction. This is the group of young people when this experiment was done in Pisa, in the Lens laboratory part, which is in Pisa, with the National Science Council, and now story is going on at Lens in Florence, where these atoms of dysprosium are excited by light to very high levels. So this is the Rydberg excitation. So Rydberg states is a state so highly excited that at the end, in that level, the spectrum seems to be the same of hydrogen. Because you are almost free from the different interaction, and here now they are starting to observe these Rydberg states, which are and to try to follow to follow the panorama of this Rydberg state that you can produce in this atom, which is, of course, much more complicated respect to rubidium or hydrogen or whatever. And I show this because if you go back to another school on Lake Como, this was on the frontier of laser spectroscopy. You can see that there a lecture. So this is a school done together with Ted Ensch, and you see Dan Kleppner at that school talking of Rydberg states. And here you see also Sérgio Roche, and the two Sérgio Roche and Dan much discussed of Rydberg atom physics. And in fact, that time in that school, you see the lecture by Dan was exactly again on chaos and related to laser spectroscopy. So always working with hydrogen, but Rydberg atoms. So we learn a lot about Rydberg atoms. This is one of the other field where Dan has been a great teacher for everybody, I mean, in the world. And we shall see what's happened now with this prosium, which is much different from hydrogen or alkali. And but I wanted to show this because these Rydberg atoms are very important for atomic quantum simulation or quantum computer. We go to atom-based quantum computers. So you know that in order to do a quantum memory, you can choose a platform, so many different system, many different devices. For instance, before I reminded one of superconducting junctions. Here I want to talk of atom-based quantum computers because you can, if in this platform you can control the single atoms. A system with atoms has a high scalability because if you do it with one atom, it's easy to do with 1,000 or even more because all the atoms are equal. There is this long quantum coherence, so very low, the coherence, and then you can couple very well one bit, to the other. So this is general true for all the atoms. The image that you see here is some work done in Florence using, again, another 2 electron atom, which is a strontium, which is a possible quantum simulator or quantum computer. And the things that you see flashing in the image are single strontium atoms trapped in optical tweezers. So each one of them can be a bit, a quantum bit. And then you can control that there is either no atoms or one atom. And there is now a very good control of this situation. So atom-based quantum computers are important because are simple, are quantum object. And so people think that the atom-based quantum computers can really be, the winner of this race towards quantum computing. For sure, the reason that I described to you, ytterbium before, is also that ytterbium atoms, as you might know, is a key atom to develop the optical clocks to measure time using the clock transition between from the ground state to the metastable state. This is a transition in yellow, and the importance is that you can connect, for instance, the Lens laboratory to the metrology institute that we have in Torino, and then you can have essentially a clock at home simply because of a fiber connection. But these clocks have now a stability, a precision better than 10 to minus 18. Okay, then you can speculate with this kind of accuracy. You can do geophysics. You can see the effect of gravity on time. 10 to 18 seconds is the age of the universe. So practically, they are missing a second, maximum a second. since the beginning, I mean, of the universe, because they are 10 to minus 18. But when we decide to go to use Ytterbium also to make a computer, the idea was that since with Ytterbium you can do clocks that they go at this level, 10 to minus 18, or now even better, means that they are very much less they have small perturbation by by the environment, because the spinner, nuclear spin, as I told you before, I mean, and so on. And so you using them for a computer means that you can have really a long decoherence time, a long coherence time, and so which is important, I mean, for a computer. And now that we have reached with time, with measuring time with optical clocks, let me show an image of a very young Daniel Kleppner with Norman Ramsey, who was his scientific father, and they are on face of a maser. And so this was around the 60s. Now, more than 60 years later, you see the improvement from a maser to from the maser to an optical clock. And we see here a very, very young Dan Kleppner, researcher. It is impressive, the progress of science. That was always hydrogen. I have already told of this ultra precision, and so now we can think to go creating, to use an Ytterbium with this long coherence time, more than 1 second. We can use it to have an electronic qubit, which is the one that I marked with the yellow, the orange line, or even a typical, the ideal two-level system that you see between 0 and 1. You can go up and down, up and down, up and down. And this is our qubit for, our clock. And now we use all the tools that we put in the receipt, because in order to do a computer, you need a qubit. Also, you need to make an entanglement between these qubits. As you know, you have to create a situation where two side qubits are, combined together. Now, if you have two of these atoms, for instance, of Ytterbium, and put them pretty close one to the other, since they are very big, being Rydberg atoms, essentially there is in the excitation you have and you shine the laser to go to the Rydberg, you can excite only one of the two atoms, because the other one is out of resonance because of the interaction with the first atom. But of course, you don't know which is the excited atom. So essentially, you have the entangled state that maybe is the first one in the excited state, or in the Rydberg states, or it is the second one. So essentially, you have the usual idea of the superposition of states. And this is a very old story, because essentially it was, as usual, Enrico Fermi in 1939, who was the the one who understood the shift of light, spectroscopic light, in a gas of atoms, simply because he understood the story of what now we call Rydberg. Is the same paper where Fermi developing the theory of the scattering length, which is fundamental importance, for instance, for the BC. And tomorrow, if you listen to the lecture of Dan, I'm sure that he will discuss this. And so, in the lab, you have seen so many atoms brought to very low temperature. You have seen experiment to test the symmetries with, with ytterbiums. So this ytterbium is promising to be a clock. And in fact, you see on the right, Leonardo Fallani showing me that we could transform the system, making it much smaller. And the other two are Filippo Caruso on the back, and on the left, Giacomo Cappellini. And so we decided to go ahead with the construction of a quantum computer using ytterbium with this ItQuanta, a small company, which since 1 year or so, instead became a very important new world venture for quantum computer, where we created a company with one of the largest, the biggest in energy industries that we have in the world, for sure in Italy. So atomic physics from the lab now is going to industry. And so I thank you for the attention. During these things, I have really been happy of remembering many of the teaching of Dan Kleppner to all of us, and of course to remember his great friendship. Thank you.
Thank you, Massimo. Are there questions for him? I may start. Do you hear me well, Massimo?
Yes.
You said that people think Rydberg atoms are the future of quantum computers. I was wondering what you think personally, with all you have seen around, if quantum computers will be Rydberg or will be.
Well, I think that we started this adventure 1 or 2 years ago. So I think that I trust. I mean, I feel that it will be possible. The story is as follows. I mean, why atoms should be better of all the others? Well, this technology with light and atom is the most recent, so there are progresses. So essentially now, in terms of qubits, atoms are going similar to the superconducting junction computer. The fidelity also is good because, the interesting thing that, for solid state device, you need essentially a culture of developing a device. And all the device must be equal, and so on. So the atoms are easier. And you don't need liquid helium, all these things. You have a huge, of course, optical accessibility. And then you can control what's always going on an ytterbium computer simply with light. And but also, you know, that there are companies which were started before with atoms. For instance, Michalukhin in Harvard or other people elsewhere in the United States, and they, or even in France, and they have started with, of course, rubidium or cesium, which, as usual, like the BC, was started with rubidium because it was an easier atom, if you want. Which, of course, they are successful. The difference is that in terbium, we expect to go further. But I mean, the results with rubidium and cesium, they are already very much showing that it is a good platform. We just started, it's the most recent which was started. So we can only expect progress.
Thank you. We have another question.
Yes.
Hello, Massimo. This is Claudio Lenz Cesar. And I remember when we first met, it was in a symposium of frequency standard and metrology in Cape Cod, I think. And I was presenting the first spectrum of hydrogen that I did with in Kleppner's
Yes,
group.
you were there.
And yeah, it was very nice. And then, you know, we met so many times around. So first of all, thank you very much for this very beautiful lecture and all these nice areas that have developed. I think we owe your generation, Kleppner, Hench, Arroche, and so many other people for guiding us to these really fantastic developments in atomic physics that now we see, I mean, all the way from this very basic science, elucidating lots of quantum phenomena and details, all the way now to industry, right? I mean, people looking forward to a quantum computer and all these clocks and all this technological application. I think this is really amazing, the development that happened all the way from, you know, these quantum simulators, these BEC, new states of matter, clocks, and so on and so forth. So I want to ask you about basic physics. I mean, where do you think big developments will come in fundamental physics? From your view, I mean, you have so much experience.
First of all, let me tell that I'm very glad that you are there. Also because I can tell to the youngest people now who are probably there, which was your answer when we met the first time. Because you were already working in that experiment of the spectroscopy of hydrogen with Dan. And then I asked you, well, how long is this PhD work? I mean, how long will you stay there? When you will finish? And then maybe you remember, you answered me telling, you know, when I asked to Professor Kleppner, when should we finish with the PhD, Professor Kleppner answered with his name. He said, then, in a sort of a future. So this is very interesting, you know, the fact that you are really to work, I mean, very hard. Then, second, now I'm here in Bern, where we gave with the Balzan Foundation a very, very important and rich prize to Christophe Salomon for the measurement of time, you know? And this is also a long adventure that was started with, you know, the fountain clock. and which since a few months is also in the space space shuttle and space station. And also this tells you or to the young that you have to start with ideas. I mean, I remember when 40 years ago, 30 years ago, there was this idea of making fountains to bring them in the space, all things which seems to be totally difficult, but now it is working. And so they have started the special test of the Einstein, general relativity, fundamental physics, and so on. And it's also this should tell us, Claudio, that science is producing technology develop and produce new science. I mean, and so on. What I have seen of interesting. Well, you have seen the picture of Dan with Norman Ramsey. So Norman Ramsey is the one who wanted to try to study whether there was an electric dipole, a permanent electric dipole in a neutron, if you remember. So there is this EDM physics, which is very much interesting. Eric Cornell, should you find an electric dipole? I mean, you would need some new physics. I mean, behind the standard model. So that is an interesting, I mean, path to be followed. And again, what I like very much is that our kind of physics. For instance, now there is a project, a new program started in Florence by Alessio Ciamei, who produced ultra-cold degenerate molecules between chromium and lithium. And then these are dipolar and so on. And he has a important project to test the possibility of an electric dipole moment. So what I think that our field of atomic physicists at very low energy can be, very much fascinating, because you can test fundamental things, maybe revolution, without using huge machines or things like this. So it's we need some surprise. And just to make another consideration, when they ask me, well, but what should be useful for a quantum computer, no? And then you start to say, okay, you can make factorization faster, you can compute faster, I mean, and so on. But the real answer is another one, that suppose that we really have a tool like this, it is a little bit like when laser was invented. Laser was not even patented, because people say, okay, is a solution searching for problems, no? Instead has been so let's wait for a quantum computer. Maybe we shall have a sort of an explosion. Whenever in physics you had a more powerful instrument, imagine the Galileo telescope, you can discover something. So there is much. There must be a lot of room for surprises. So this is my hope for all the young people now entering the field.
Excellent. Thank you so much, Massimo. Very nice to see you and to hear you.
Arrivederci.
Massimo, I don't see further questions, so I would like to thank you very much again for giving your time to give us this wonderful talk. I hope we can bring you back here once again in the near future. Thank you very much.
We should meet in person.
Yes, so let's thank Massimo again.
Ciao. Tell me.
We have a short break. We come back at 11. Okay, thank you for coming back. We have now Cláudio Lancesa from Federal University of Rio de Janeiro and CERN, I think, and Impatec, also from Rio. He will talk to us about anti-hydrogen. So Cláudio, thank you a lot for accepting our invitation, and please, the stage is yours.
Well, thank you very much, Emmanuel, for this invitation, Vanderlei, the whole team. It's really a pleasure to be back here. I used to come here very often before the pandemic, right, for a thesis, for talks, for interactions, but then I haven't been here since the pandemic, so it's really nice to come back here. Especially in this fantastic occasion in honor of Dan Kleppner and quantum mechanics. I prepared a small preamble, two slides on quantum mechanics and atomic physics. Well, you know from the history of physics that Rutherford was the one that pointed out that most of the mass of the atom was in the nucleus, and the nucleus was very tiny. And so later, this developed into quantum mechanics, starting from Bohr in the old quantum mechanics, where he proposed that the orbits were quantized, were discrete, and an electron could absorb light and go up in energy level, or emit light coming down in energy level. And you think this is trivial, but it is really fantastic, because it means that the atom has these very discrete absorption or emission lines. So each atom has a digital signature, let's say, okay? So we can identify each atom by this light that it emits, because it's a very good resonator, all right? And of course, by the Doppler effect that you all know from Sheldon Cooper from the Big Bang Theory, we can look at very distant galaxies and see absorption lines and emission lines, and we can find out the speed of stars in galaxies, and we can map out how they rotate around a galaxy, for instance, okay? And by finding out these speeds, we can infer the gravitational attraction that these stars feel in that galaxy. So that this way, it's funny, we look for stars which are 1 billion light years away, and we can find out their chemical composition, and we can find out a lot of that story and the mass that is involved. So this all comes from the fact that each atom has a very specific signature in these quantum levels, because each atom is a very good resonator. And this is the basics of laser spectroscopy, actually, right? Of course, this development, we know that Schrödinger's quantum mechanics was not complete, and Dirac came with his equation, and that solved the fine structure in hydrogen, the splitting between the 2p level, the p1/2 and p3/2, for instance, follows exactly Dirac's theory. But it's not all the story. Dirac was very bold. He proposed that from his equation you get a square root, and he proposed that all the terms with negative energy, they were like a sea of electrons with negative energy that you would not see, you would not interact with them. But if you come with energy, you can promote these electrons that we don't interact with, this sea of electrons, and then a real electron appears, and a hole appears in that sea, and that hole behaves like a positive particle. So you get a positive kind of electron and a negative electron here. This was Dirac's proposal, and soon after, Anderson detected the positron, and later, Segre and Chamberlain detected the antiproton in Berkeley, and this opened up the whole era of antiparticles. And we know each particle has an antiparticle, and we can even make exotic atoms or even anti-atoms, okay, with these antiparticles. Of course, even Dirac's equation was not complete, and Lamb, with a series of experiments with hydrogen, so hydrogen has been very important in this development of quantum mechanics, atomic physics, our basic knowledge of nature. And Lamb showed that the 2s 1/2 and the 2p 1/2 levels, they were not degenerate, which Dirac's equation predict, and they are not degenerate. And that was one of the main motivations for the creation of quantum electrodynamics, which is by far the most tested, the most accurate theory in physics. Okay, quantum electrodynamics can calculate the energy levels of hydrogen and antihydrogen to 12 or 13 digits, significant figures. And that fits exactly well with the experiments. So it's an amazing theory, okay? Well, so Dirac basically doubled our universe of particles because of antimatter, okay? Now, of course, it's not, we don't use this C, it's basic in the basic consistency of quantum field theory that you need these antiparticles. So let me now go for my talk. I'll talk about antihydrogen and a few other things, and then I'll also show a little bit of the experiment I did at MIT under Dan Kleppner, and also a few bits on the experiments in Rio that we're doing in Rio. And here's Dan Kleppner, Beatrice Kleppner, I and my wife, in Recife in the International Year of Physics 2005, I guess, okay? And it was really a fantastic privilege to work for 7.5 years under Dan Kleppner. Massimo said that my PhD took a long time. Indeed, it was 7.5 years, but it was really a fantastic time. This man was a really source of inspiration, okay? Very wise person, very nice. I'll show a few things. I'm not going to show much of the history, but I'll show a few things. And of course, dealing with Beatrice Kleppner, for those of you who had the chance to meet her, she's just a fantastic person. Okay, I have a story that I can tell at the very end. So let me talk about antimatter. So in the beginning, let there be particles. Matter and antimatter were created, but somehow the primordial antimatter disappeared. So maybe the devil went there and took it away, okay? And so the idea we have about the universe right now is this Big Bang. We created, from this big explosion somehow, all the universe was created. This whole thing expanded, and gravitational attraction made galaxies and stars and planets and so on and so forth. But somehow now, today, we look at the universe and there is no primordial antimatter. There is not a single star made of antimatter as far as our observations go, okay? But in the very beginning, as far as we know from physics, there should have been created almost as much antimatter as matter. So somehow this balance is not balanced anymore. Something happened. There are many ideas, crazy ideas, like the mirror universe, that a whole universe of antimatter was created and it's somewhere else, okay? And I mean, there are many ideas. As far as we know, CP violation is not enough to explain our universe. And so we don't have a good scientific explanation for our universe, okay? The Big Bang is the best we have, but it's a story that you can tell your kids to go to sleep, okay? It's not a full story. So we have lots of things to do in physics. Physics is not completed. This is for the young generation, and we have lots to find out, okay? Just a bit of a history. Physics believed in these discrete symmetries. Parity. Parity is when you inverse, you inverse the space, okay? And physics believed that in all these microscopic things, parity would be conserved. And Lee and Young proposed a mechanism by which parity was not conserved, and Dr. Wu saw that, and that gave them the Nobel Prize for P violation. Later, physics believed that if you do a charge conjugation, so you go from matter to antimatter and vice versa, and you reverse the space, then that would be a good symmetry in physics, and that's called CP, symmetry. And Cronin and Fitch saw the CP violation, the K-on system. And now physics believe that if I change the charge, I inverse the space, I reverse time, then CPT is a good symmetry in physics. It's a good discrete symmetry. And of course, this is proven, but in a flat space, does not involve gravity, and so on. And some of the predictions of CPT is that particles and antiparticles should have exactly everything is the same. So they except from the change in charge, right? But the modulus of the magnetic moment should be the same. If I make an anti-atom, all the energy levels should be the same. The lifetime of the energy levels should be the same. Everything should be just the same. Okay. Very good. And this is in the base of the standard model, SM, standard model. But do we have any reason to believe, to doubt the standard model? Well, there are quite a few reasons to doubt that the standard model is at least incomplete, okay, and at most wrong. But I mean, it's a very nice theory, but it's a theory. We have to test against the measurements. I'm not going to go through this, but there are many issues. So, long time ago, we decided to test CPT by comparing hydrogen with anti-hydrogen, okay? And basically, I had just completed this measurement under the group of Dan Kleppner and Tom Greytak at MIT, where we did 2-photon spectroscopy of hydrogen in a magnetic trap to a very high precision. We had a resolution of parts in 10 to the 12. At the time, there was no frequency comb, but in principle, if we had, we could have accuracies of parts in 10 to the 15 or beyond, okay? And later, the group of Ted Hench, and here's Christophe Salomon that was just mentioned, and Tino worked with him, so this group, this French-German group, they do hydrogen spectroscopy to 4 parts in 10 to the 15. This is absolute measurement against the clock, against the time, against the standard of time, which is the cesium clock. Using the frequency comb, they can do this matching. So, in principle, you can do hydrogen to very high precision, and we could imitate the ideas with hydrogen, with anti-hydrogen, and try to get a comparison between matter and antimatter, 2 parts in 10 to the 15, 16, 17, maybe 18, okay? That's the idea. So, some other systems have been compared, matter and antimatter. For instance, the electron, the positron magnetic moment, the proton charge to mass ratio, and the antiproton, and magnetic moment, and so on and so forth. But we can do better than all those experiments so far, okay? So the basic idea of this experiment is to, here's a hydrogen atom, here's an anti-hydrogen atom. You shine a laser in the anti-hydrogen, you excite the 1s, 2s transition, which is a transition with the highest Q value, highest quality factor, so it's the highest precision. And you shine the same laser in hydrogen, and you ask yourself, when they absorb, is this frequency the same? And the energy levels of interest are the ground state of hydrogen, 1s state, the 2s state. This state is metastable. It lives for 122 milliseconds. So you can literally watch it and time with your cell phone, right? Because it's 0.1 second, okay? It's very long-lived. And this transition is in the ultraviolet. So what happens from this level is you can mix into the 2p state by a small electric field, and then it decays emitting a Lyman alpha photon, which is 121 nanometers. It's vacuum, UV. It doesn't propagate in air. Or the same photon from your laser is also able to ionize this atom. Okay, so people have used different methods to detect hydrogen based on this. And of course, since we propose to make anti-hydrogen, it's a neutral antimatter, We of course thought, well, let's try to drop antihydrogen. Since it's neutral, we can try to drop and measure the gravity acceleration of antihydrogen. So this was in the initial proposal of Athena and then later Alpha. And the question is G the same? And here, is the frequency of hydrogen the same as antihydrogen? Those are genuine questions to ask, okay? And of course, one can go beyond models and theory. It's a nice, different material than anybody has. So we have the obligation of checking everything about this material, right? Okay. Let me show you a slide from Randolph Paul, who also worked with Ted Hench in this measurement. The 1s, 2s transition. If you just do the Bohr theory, this is the distance between the levels. If you include Dirac equation, then you get shifts on these levels. If you include lump shift, QED corrections, then you get also shifts. And then if you include the hyperfine splitting, and you put in a magnetic field, and so on and so forth. Now, finally, this transition is an S-state wave function, and people who have studied quantum mechanics already know that the S orbitals, the electron penetrates the nucleus. So this transition is sensitive to the proton size. And how much is that? That's about 1 point something megahertz, okay? Around 1.2 megahertz. So when we measure anything in the 1s to S transition better than a megahertz, we are already also probing QCD, quantum chromodynamics, the structure of the proton. Well, we are not probing QCD because QCD cannot predict the nucleus yet. But they are working hard, and eventually they will come up with a model that you can quantify the proton. Okay? And in that case, we already have the experimental data to test their theory, okay? So how you make antihydrogen? Well, we make from the constituents. We start with an antiproton and with a positron, and we have to bring them together to make an atom, to bind them together, okay? Now, the antiproton is made at CERN in an accelerator. You take a proton, you accelerate, you hit a target. If it has energy much higher than GeVs, you can create pairs. You can create protons and antiprotons, neutrals and antineutrals, and so neutrons and antineutrons, and so on. Okay, and CERN has made one decelerator. It has many accelerators, but only one decelerator where it collects these antiprotons and decelerate for us. It started that for 3 experiments. We were one of them, Athena, at that time. And then CERN sends us the antiprotons. And so it takes a lot of energy to create these antiprotons. And what we do with them, we pass them through a degrader, through a window. We annihilate 99% of them, unfortunately. CERN spent a lot of energy and money to generate lots of antiprotons. And the first thing we do is we get rid of 99% of them. But a small fraction passes through this window, this solid window, and lowers its energy. And then it comes into our trap at energies which are in the kilo electron volt range rather than in the mega electron volt range, okay? And in that case, they come into a big magnetic field, this solenoid, somehow the connection, I think this thing sometimes has problems with some projectors. Okay, it came back, cool. And this big magnetic field on axis here makes the particles cycle around the magnetic field. So it basically restricts the particles radially, okay? And we put a potential here. Antiprotons are negative, so we put -5 or 3 kilovolts now, -3 kilovolts. If the antiprotons have less than 3 kilo electron volts, they will reflect. These are rings, ring electrodes. So this is in ultra high vacuum. I have a ring, I put -3 kilovolts here. And here's ground. So if the antiprotons come in at less than 3 kilo electron volts of energy, they will electrostatically reflect. And as they try to go out, I close the door. I turn on -3 kilovolts in the other electrode, okay? And then they remain trapped and they can't go radially because of the magnetic field. So they do this kind of a spiraling figure typical from penning traps, okay? One of the traps that is also used for precision measurement of masses of particles and also for quantum computing as well. I'll talk about that later, okay? Now, the antiprotons come in, but they're still at very high energy. 1 electron volt is 10,000 Kelvin, okay? And so what we do is we put electrons in here. They are not antiparticle of each other. And the antiprotons collide with the electrons. The electrons are very light. They're leptons. And their orbit around the magnetic field has a very high acceleration. So they emit radiation like crazy. So they cool the antiprotons very quickly, okay? It's called electron cooling. Very good. In the other side of the experiment, we have a radioactive source that emits positrons. You know, you all have a positron source in your body. I mean, raise your hand those who do not eat bananas here. There's nobody. Everybody eats bananas or Brazil nuts, right? As castanhas do Pará, okay? They're full of potassium-40, and this potassium-40 decays. It's a radioactive nucleus, and it decays and emits positrons. So you are a source of positrons inside your body, okay? So this is not, you know, but here we make a source from there's a company in South Africa specialized in this, makes a very strong source in sodium-22 and emits positrons, and we have a neon moderator on top, and that's where I got one of my ideas that I developed in Rio, this neon moderator, a solid neon moderator. And so the positrons come in, they come continuously. And we have another penning trap, but in this case, it's a penning trap that continuously keeps the positrons. How? By collisions with nitrogen gas, they can lose energy and go to lower and lower and lower energy, and they accumulate where the gas the pressure is the lowest. Okay, it's called a differential pumping system. The pressure is lowest here, and the pressure is higher here, and then they can lose energy and accumulate. So we make positrons with that. And finally, we bring antiprotons and positrons together to try to make antihydrogen. And how we detect, the first time, we just had an annihilation detector. And the first time we had annihilation detector, there was silicon, and that measures the pions. Okay, so when the antiproton annihilate with the material on the walls of our electrodes, it emits these charged pions. These charged pions, they leave charge in these silicon plates, okay? And the silicon has lines and columns. And so you have pixels in the silicon that you can read, you can amplify, you can read, and the computer can know exactly in a very short time that a pion pass through here, deposit charge here, here, another one deposit here, and then I can retrace this ray. And for instance, in this case here, it looks very much like a cosmic, because a cosmic particle can come in a line like that. So I would reject this count. It's not a real count of antiproton, okay, typically, okay? We train it with machine learning, okay, this detector. We leave it not with antihydrogen, and we let it train for days. We collect all those events, and we say, all those events you looked at are not antihydrogen. And then it gets trained on what is antihydrogen. And then when you put in the antihydrogen and let it annihilate, then you create things like that. For instance, in this case, 3 pions, and you can recreate the vertex. So these rays, they come to the same point at the same time. So we know that an antiproton annihilated there, okay? In our first detector, we also saw the gamma rays from the annihilation of positron and the electrons in the wall. Here, this time now, we only have this silicon detector. So, but we want to do precision measurement. And there's no way you're going to make an antihydrogen atom. It's going to come out flying like crazy that you can do a high precision laser spectroscopy measurement on it, okay? It's like you go to the highway here, Washington, Louise, and you were looking at the cars passing by, and if they pass at 120 kilometers an hour, you have barely a chance of seeing the color of the car or seeing how many people are inside. you can't know the details. This is something like Fourier transform. You have to observe for a long time to get a high precision measurement, okay? So the only hope for us to do a high precision measurement is if we can trap these atoms first, okay? And of course, this is the trap that we used at MIT to trap hydrogen. It's called a Yaffe-Pritchard trap. You have mirror coils here, mirror coils here. So the magnetic field in this axis, the z-axis, it has this profile, goes through a maximum under this coil, a maximum under this coil, never goes to zero. And then we have 4 current bars, called so-called quadrupole, that creates a field that grows in the radial direction. So the modulus of the magnetic field here is always different from zero. It has a minimum, and it grows in all the directions. And this is what we call a magnetic bottle, a magnetic trap, okay? And it can trap the species where the energy, the potential magnetic energy of the atom grows with magnetic field. These are the so-called low field seekers or low field seeking states. Why? The energy grows if you grow the magnetic field. So everything in nature tries to go to lower gravitational, lower potential energy, right? So these atoms get attracted to the minimum field, and these are the ones we trap. Okay, so they are not really fully ground state. They are hyperfine excited states in the ground electronic state of the atom. These guys here, they will be attracted to high fields which are in the walls. So these are not trappable, okay? Now in alpha, we use a kind of a Yaffe-Pritchard, but instead of a quadrupole, we use an octupole here. And the reason is we have to manipulate plasmas of electrons, of positrons, of antiprotons, and if you have this Yaffe-Pritchard trap, the quadrupole, that field is going to bring these particles out to the wall, and they affect the pinning trap. So that's why in the center, we have to keep the field, this radial field, almost zero. So that's why we go for an octupole, okay? This is a picture of the antiproton decelerator at CERN. Here I and my students. This is a present PhD student. These are 2 previous PhD students. And the alpha experiment is here. So the beam, the antiproton beam in the AED, it circulates under these concrete blocks, okay? Goes around here in this hole. And from time to time, each experiment, here there still exists a trap, and there is a Asakusa in the other side, and here's our experiment, which is now called alpha, okay? So this was created for these 3 experiments. Now a trap is not there anymore. So we get a beam of antiprotons, and then it goes into our zone here, which is this region here. So that's where we trap the antiprotons, and then in the other side of the zone, we produce the positrons, and then we bring them together, mix, make the antihydrogen, and then trap them and do laser spectroscopy, okay? Just to give you an idea of the timing here, in 1997, after I finished my PhD at MIT, Kleppner went to a symposium in Denmark, and someone approached him saying, look, we want to do like you guys did at MIT with the hydrogen spectroscopy. Would you like to join us to make antihydrogen? And Kleppner looked and said, oh, look, I think you guys can contact Claudio in Brazil. He just went back to Brazil because I'm too old to get into this new thing, and I think you can contact him. So I got into this because of Dan Kleppner, okay? It's very important that you keep a good relationship with your advisor, okay? Always, okay? So in 1997, we founded Athena, and we promised, well, you know, like the promise of the clock that you got from the space agency, right? In 3 years, it's going to be done. So we promised in 3 years, we'll be doing laser spectroscopy of antihydrogen. Well, turns out we made the first antihydrogens ever at low energy in 5 years afterwards. And then we found out they were too hot. Then the collaboration split. We started a new collaboration called Alpha. And we were able to trap antihydrogen in 2010, and then in 2018 we produced the first spectrum of antihydrogen. So it's quite, this is a lifetime experiment. And that's what happens with some experiments. It just takes a lifetime, okay? And then we were able to do laser cooling, and we were able to do the first gravitational fall of antihydrogen. And now, this year, we should have many new results in press. I mean, we are finishing all the papers, and I'll show you some preliminary ideas. So let me show you a little video, because a picture says more than 1,000 words. That's what they say. So this video should enlighten you on our experiment. So this is our detector. It's about this big, okay? 30 centimeters. 3 layers of silicon. It costs only 3 million pounds, sterling pounds. But it's a tiny thing for CERN. CERN is used to the detectors that you can go inside. Now, if you take off this detector and goes inside the liquid helium, then you get to the superconducting inner magnets. And this is all inside a big superconducting magnet, one of those for tomography, for MRI, okay? Now, if you go here, you're going to see our trap, so the mirror coils and the octopole. So with this configuration, we have a magnetic field that's minimum in the center and grows in all the direction. Now, inside this tube, that's ultra-high vacuum, and this is all at 4 Kelvin. Now, if I open inside this tube, I'll see the electrodes that I use to manipulate the plasmas, the electrons, the antiprotons, the positrons. I put my electric fields and I go with them here, there. I do all sorts of stuff, okay? So, for instance, if I accumulate positrons here, this is a plasma, billions of positrons, then the antiprotons are here, few of them, and I send them very slowly through the positron cloud. And then in a 3-body collision, one antiproton with 2 positrons, this antiproton can capture the positron, and the other positron takes the excess energy and momentum, okay? And then you form a Rydberg antihydrogen, but this Rydberg antihydrogen, if it has the right magnetic moment, it's trapped in the magnetic trap, this bathtub, and it remains there, and then it decays all the way to the ground state. Some do not survive, but some of them survive, and they're trapped if the kinetic energy is very little compared to the magnetic energy, okay? And then if we open the magnetic field, then they are free, they hit the walls, they annihilate, and they produce these charged pions that give us signal in the detector, okay? And now we detect antihydrogen with 80% efficiency, each one of them, okay? Now, we want to do laser spectroscopy, but there is no powerful laser enough for that. So we had to make a cryogenic cavity. Actually, this was made by us in Rio, where we take a laser, the 243 nanometer laser, and we enhance this power to a very high value of power in the beginning, okay? And then the atom can absorb 2 photons going from the 1s state into the 2s state. And another photon can photoionize. And that's one of the principles of detecting this antiatom, okay? That it absorbed the laser, and we can vary the laser frequency and see when the atom absorbs. And that's called spectroscopy, laser spectroscopy, okay? Good. What we want to do with antihydrogen is something like we've done with hydrogen. And this is the result from my PhD with Kleppner. This was hydrogen in a trap, in this case at 400 microkelvin, which is slightly cold. The goal here was to reach Bose-Einstein condensation. And so the experiment was not optimized for optics. We had very little detection efficiency, very little solid angle for detecting, but it was optimized to reach Bose-Einstein condensation. And if you look, we have about a few kilohertz line width, okay? And I'll tell you later about this theoretical paper with I and Kleppner, where we reinterpret the transit time broadening with a transfer of momentum, a transverse transfer of momentum when the atom crosses the laser beam, okay? And so when you hear about Ramsey fringes or Fourier transform, okay, be careful, because in the Fourier transform you say, well, the atom is crossing the laser beam, so it saw the laser beam for a short time. That means it sees the laser beam broadened in frequency. That's just wrong. I mean, it's Fourier transform, you do that. But if you try to justify how come the atom absorbed a photon at a frequency that did not correspond to the right frequency, that didn't preserve energy. And the reason why that happens is because when you cross the laser beam, you can absorb at different frequencies from your resonance because you get momentum kicks from the transverse of the laser beam. So if the laser beam is finite, then you have a finite time of crossing the laser beam. But that means if your laser beam is finite in size, that means it has transverse momenta as well. And this exchange of transverse momenta is what explains you to have absorption in frequencies that do not preserve, would not preserve energy. If you take into account this added momenta, then you preserve momentum and energy beautifully, okay? And this is the same, is also true for Ramsey fringes, okay, and so on and so forth. So be very careful with that. And I also later extended this paper to show in the presence of the magnetic field of the trap, where some atoms are at one field, some other atoms are at another field. This was an inspiration from Kleppner. And it turns out that this transition gets broadened by the fact that at different fields, the frequencies are slightly different. But luckily, the 1s, 2s transition hydrogen is almost field independent. And the reason is that the magnetic moment of the 2s state is almost the same as the magnetic moment of the 1s state. There is a relativistic correction, okay? And so this adds very little broadening to our system, and I showed that it's possible that we get to the range of super spectroscopy, really to go to parts in 10 to the 15 in resolution. So in principle, you could resolve your line and go to parts in 10 to the 17, 18, and so on, even in a magnetic trap. Very good. So after many years, finally, here comes the first spectrum of antihydrogen. 12 significant figures. By the way, this is the most accurate measurement so far on antimatter, okay? And the size of our collaboration is this, about 50 people, including the students. We are now getting very nice enhancements. One of them is here. Guilherme Tino is going to join us, and Holger Miller, to try us in the future, to try to help us in the future to do laser interferometry gravity with antihydrogen. So let's look forward to that. So this is the cavity here, the cryogenic cavity where we shine the laser, the many electrodes, the many magnetic coils here used, and all of this is inside a big solenoid, an MRI solenoid. So we trap the atoms here in the magnetic trap, we shine the laser, and we do the spectrum. And this is the first spectrum of antihydrogen, and it was done by two different methods. And if you look at the frequency we measured with 2.466 and so on kilohertz. Okay, this number is so beautiful that it's in one of my secret passwords for the bank. Okay, I use some of this number. And of course, if we take hydrogen from Ted Hensch's measurement, and he does that at 0 magnetic field, and then we use atomic theory, all what we know about Zeeman and diamagnetic correction, so on and so forth, and we calculate what his number measured in hydrogen would be in our environment. Then you get this value for hydrogen. Oops. And the two agree to 2 parts in 10 to the 12. So this was at the time the best comparison between meta and antimatter. Very good. So, but if I take the alpha spectrum of antihydrogen and I put here the 30 years before that, the hydrogen spectrum that we did at MIT with Kleppner, then you see that the anti-hydrogen has a lot to progress yet, right? Because our atoms were at around 300 millikelvin, okay? While our anti-atoms and our atoms were 400 microkelvin. So we are far from exploring or exploiting fully this quality factor of this transition. And here, I mean, I did this in an international conference just last month in France, the European Nuclear Physics Conference. This paid this tribute to Kleppner. I mean, that's a person who made the first hydrogen maser with Ramsey. Today, every single place where you have high precision measurement uses a hydrogen maser, okay? He was so into increasing these resolutions that he thought, well, okay, the ultimate resolution is in part, it's set by the natural line width. It's restricted by the natural line width. Of course, some atoms live longer than that natural line width, and you can exploit that, but that puts a small first limit to how much you can improve your measurements. So he thought, why not inhibit spontaneous emission? And he had this idea. He couldn't do it immediately, and he always told us, it was funny, he didn't like publishing papers just with ideas, because he was an experimental physicist. He said, if you have an idea, you go to the lab, you show it, then you publish, okay? But in this case, he said, well, when you can't do that immediately, then you can publish, okay? So he published that idea of inhibition of spontaneous emission with the atoms, and indeed, work done at MIT, at Sérgio Roche's group, and so on. That was the beginning of cavity QED, which is a very nice area where you restrict the modes of your vacuum, and with that you can inhibit or enhance spontaneous emissions. And of course, he very soon found out that if you inhibit spontaneous emission, you get couplings and you get shifts. So it's no good for high precision measurements anyway, but that was his initial motivation. But he also did, a master work with Rydberg atoms. Massimo Inguccio already mentioned that, and a lot of work in quantum chaos. I think Jarbas from here was his PhD student, Jarbas Castro Caiado, and he worked on this quantum chaos experiment at high magnetic and electric fields. Okay, he was the father of evaporative cooling with atoms. That was invented in his lab at MIT. It was an idea of a postdoc called Harold Hess, and he's considered one of the BEC fathers. And eventually, our experiment, which didn't succeed while I was there, but just 2 years after I left, reached Bose-Einstein condensation with hydrogen. It was the most difficult experiment with Bose-Einstein condensation, but it's still the biggest Bose-Einstein condensation ever produced. At 10 to the 9 atoms, and so on and so forth. Anyway, this is the figure of Dan Kleppner, which I miss very much. So let me continue with the anti-hydrogen. We eventually developed Lyman alpha cooling of anti-hydrogen. This is a tour de force experiment, because nobody has cooled anti-hydrogen or hydrogen before trapping, okay? In hydrogen is the opposite of the other alkalines. In the other alkalines, you cool them with lasers and then you trap, okay? In hydrogen, you have to trap first and then cool, because producing Lyman alpha photons is very hard, okay? The numbers you produce is very little. And, okay, I'm not gonna describe, but that experiment to Lyman alpha cool takes a full day, almost, laser cooling. So we have a very good vacuum to accumulate anti-hydrogen and laser cool it for a full day. It's like 24 hours experiment until you have your sample ready to study, okay? Let me show you very quickly I'll just pass through this. This is too much detail. But if you have the photons coming counter-propagating the 2 laser beam to avoid the first order Doppler effect, the atom crosses here, and then you get this this time of flight broadening line shape that was first given by François Birabin in France, they're called normal, and we reinterpret that at MIT as fact of exchange of momenta, transverse momenta with laser beams. But now we are in a different regime, not that quantized regime that I used at MIT for alpha. We are not yet that code. So I and my PhD student Levi, we did a little theory on a line shape where we include the AC Stark shift, we include ionization, and the idea here was to produce an analytical line shape, because the way we interpret our data was based on a quantum Monte Carlo simulation that takes a whole week to simulate, and you get a few points, and it's very hard to interact with that. So we produced this line shape. It's published in PRA, and it's valid under these conditions. It turns out that this works quite well. We predicted parts in 10^14 of accuracy of this line shape in our magnetic field. And indeed, this is a simulation, and you show data simulated by Francis, who's a very careful theoretical physicist, atomic physicist. And you see that our line shape produces exactly, okay, the right fit to those simulated atoms that he simulates for, you know, the atoms stay there forever in the trap, and you have to simulate that in the interaction with the laser beam, solving the full optical block equation, so on and so forth. So we are getting parts in 10^14 of accuracy with our theory, and it is with that theory that we are analyzing the data now from alpha, and we should unblind finally. So the simulation was blinded in the beginning, and then we predicted the number that he put in, and he looked in the computer and got the number right. So our simulation, our line shape predicted the right number for the frequency, and now we are ready to unblind. I think next week or the one before, the one after, we're going to unblind the real data from 2023. But we already know the uncertainties, and we are going to be able to publish a data with a slightly under parts in 10^13 on this transition anti-hydrogen. Okay. And interestingly enough, one of the things that will come up soon is that the theory for bringing the value for hydrogen and putting into our magnetic field of 1 Tesla, the theory is not complete to better than 30 hertz. So we are talking to our quantum electrodynamics theories colleagues to tell them, look, you're behind us now. Okay. So they have to do work to make extra corrections for us to be able to eventually compare hydrogen and anti-hydrogen by that way, by taking the number from Ted Hedge in zero magnetic field and predicting from theory what it would be in our magnetic field. So the way we want to proceed, and I have been telling this for many years already in alpha, and I published this paper quite a while ago, where I proposed a method where we can trap hydrogen in our trap, but detect it. Because so far, we've only used annihilation to detect the anti-hydrogen. So our trap is not made for detecting Lyman alpha. We don't have solid angle for detecting Lyman alpha. And how would you detect? And this method is good for other transitions as well. So the basic idea is you put hydrogen in there, and before doing the laser interaction, you reestablish a very shallow penning trap, and you shine the laser, and then when the atom absorbs and photoionize, you keep the antiproton. And you keep for the 2 seconds that we interact at each frequency point or longer. And then after that period, then you just dump whatever you have in the trap, charged particle now, onto an MCP. And MCPs, or microchannel plates, or channeltron, they detect matter as well as antimatter. And we just proved that in alpha. One of the postdocs took the effort to do this experiment, this proposal that I had proposed, and indeed, this is a signal with antiprotons now, anti-hydrogen, using this technique. So very soon, we'll be able to put hydrogen in the same trap as we have now, anti-hydrogen, and do just a direct comparison. So we can do spectroscopy of hydrogen, and then spectroscopy on anti-hydrogen, spectroscopy on hydrogen, anti-hydrogen, and compare that directly. And in that case, we don't need the theory anymore, because we'll be in the same magnetic field, we'll be in the same laser power fluctuations, same gravitational field, same orientation in sidereal orientation, which is important for CPT, and so on and so forth. So this is very exciting. This paper is ready. I don't know why it was not submitted yet, but should be submitted very soon. All right. One word about gravity. In the very beginning of Athena, there was a meeting in Italy, in Sepino, near Rome. And at the time, 1996, people were talking a lot about anti-gravity. And there was a lot of speculation about maybe antimatter will fall up instead of falling down. Of course, after that, lots of tests of general relativity with clocks in space and so on and so forth. Of course, people got a lot of confidence in general relativity. And this would be totally out of question that you would get an anti-gravity. But in any case, I proposed an experiment, very simple, where you would, with lots of details on how difficult it would be to do it. So if you have trapped atoms in a vertical trap, and if you can match the magnetic barriers on the top and in the bottom really well, but you have to do a very good job in matching these fields, then if you very slowly open these magnetic traps, the magnetic barriers on top and in the bottom, particles would leave upwards or downwards depending on the gravitational acceleration they feel, okay? And it turns out this experiment was built with money mostly from Canada and from Aarhus as well. It's a very big experiment, very high. Here I am on the construction of this alpha G experiment. And we did the experiment, and we found that anti-hydrogen indeed falls. Of course, it has to fall. Otherwise, it would be too much. This is a little video. I'll just show you some detail. This is the antiproton decelerator. This is our experiment, the alpha 2, where we did the laser spectroscopy. And here is where we drew the gravity fall of anti-hydrogen, okay? I'm not gonna let this go for a long time because otherwise. So we get positrons, we accumulate, and then we send them, guide them with magnetic fields and make them make a turn, go into the other trap, penning trap, hold them here. We get anti-hydrogen, we trap first them here, cool them, then send the anti-hydrogen to alpha G, they make a turn, go upwards, and then we trap antiprotons in the side of positrons, then we mix them together. When we mix, most of them have too much energy, they annihilate, okay? As soon as we bring one near the other, most of them annihilate, but they make anti-hydrogen, and then they're not bound by the penning traps, only by the magnetic trap, which is very shallow, it's a very weak trap. And so lots of these guys annihilate, creating signal, but some of them remain trapped. And then we slowly lower the barriers up and in the bottom to see if they fall up or down, okay? And we did this measurement, and we can add extra bias magnetic field in the bottom, in the top, so we can add more field on the top and they all fall down. We can add more field on the bottom and they all fall up, and we can map this with the magnetic field we put in there, and it turns out that we can completely rule out anti-gravity, totally ruled out, okay, by 7 sigma. But the gravity acceleration we measure is 0.75 g, okay? So you can ask me later, why is it falling? So it's slightly slimmer than we expected, right? I mean, no, it's our uncertainty is quite high, okay? It's about 0.25 or so. So we have to get better in doing this measurement because we want to see if G is the same. So let me just flash a few things about the experiment at MIT. Kleppner was this kind of person who always, had a lot of social interaction. So one time I was visiting him with my kids, my older kids, and he put together this party for us when we were there. This is just yeah, somehow the projector, this is a, so in his house here, Kleppner and Beatrice, this is my daughter, Leticia, and a few people he invited. You can see Catterley, Doyle, Tom Graytak, and Zoller, Peter Zoller, yes. And here's Dale Freed, who was just after me in the group at MIT. John Doyle was before me, he graduated before me. And here's B. Kleppner, took us to eat some lobster and go for some trips around. So just to give you a flash on the experiment at MIT, we used a dilution refrigerator, helium-3, helium-4, which reaches 10 millikelvin. It's a big machine. Lots of problems with cryogenics. And, but we have a 4 Tesla field, and then the field lowers. And here, this is the region for the trap. It's a very long trap. And this is the lower mirror, the lower pinch coil. And so we discharge frozen hydrogen here on the walls. We have an RF discharge, send some RF pulses, and there is hydrogen frozen, and this whole cell was covered with superfluid helium. And hydrogen has a very specific thing with superfluid helium in that it has a very small bound state of hydrogen inside superfluid helium. So it has a very big probability, a hydrogen hitting a superfluid helium wall, it has a very high probability of coming off, losing energy and coming off, and not staying at the surface. Any other surface, it would stay in there. And this is very specific of hydrogen. We tried this with deuterium, and it didn't work, okay? And so if you shine the discharge, you get vapor pressure of atomic hydrogen and helium, and they thermalize, they hit the walls, and then eventually you get trapped atoms here. And later, then, we open up this magnetic trap and do this evaporative cooling. And you see, we only had 10 to the minus 4 solid angle for detection of the Lyman alpha here in a microchannel plate here after passing through a window. So in total, we had a 10 to minus 6 detection efficiency, which is, so hydrogen is very easy, it's very abundant, but the detection efficiency can be quite tiny. While anti-hydrogen is very hard to produce, it doesn't exist naturally at all, but we can get almost 100% detection efficiency. So anyway, and the funny thing about hydrogen is so light, the photon is so energetic, that if you do a Doppler-free excitation, you get no momentum kick, it's a Doppler-free, and you get a very narrow line. But if you do a Doppler-sensitive excitation, you see it's shifted far away from the Doppler insensitive because it gets a momentum kick of the 2 photons in the same direction, okay? All right, and we could measure for the first time the lifetime of the 2s state. So this is not the final measurement, but it puts a limit. And we measured 110 milliseconds. The prediction is 120 milliseconds. Of course, if you want to get to 120 milliseconds, you have to get rid of all these stray electric fields in the system, okay? Of course, this work led to this, theory on understanding this time of flight broadening. I'm not going to describe that. So let me give you a few words. What time we have? 12. Okay. Just a few words about the things we do in Rio. We have developed this technique called matrix isolation sublimation, where we send a neon gas onto a cold substrate, sapphire substrate, and then with laser ablation we can implant atoms here, atoms and molecules. And by giving a heat pulse, we can release these atoms at, say, for instance, here is lithium, at 700 millikelvin with a speeds of 150 meters per second, for instance, into ultra-high vacuum. These are just pictures on the setup. This is the matrix growing. We can see the thin film interference, typical of optics when you grow thin film on mirrors and windows. And when we do laser ablation, we get these ablation plumes, which are quite beautiful, implant the atoms into the matrix. And later we can do, for instance, 3 ablation pulses in a big matrix. And as we sublimate, we get these lines of lithium, for instance, here, okay, where we can do spectroscopy of these atoms. So we've shown that we can get almost 0 forward velocity, which is good for trapping. We'll try to trap hydrogen in Rio with that. Or you can get a nice beam for spectroscopy. We've shown that if we put lithium and calcium, or lithium and carbon, or whatever, any other thing inside the matrix, you can make molecules inside the matrix. One atom fall on the side of the other one, and it forms molecules. So you could form molecules that do not exist at room temperature. For instance, van der Waals molecules and things like that. So we showed that only with lithium and calcium, showed the production of many different molecules. And finally, we decided to set up a penning trap, and the idea was to introduce, the idea was to produce a cold beam of H- to put into alpha. This was the original motivation. So the idea was to laser ablate lithium hydride, you introduce lithium and hydrogen, and later we would produce photoelectrons with a UV laser, put them into the matrix, and they would form H-, okay? It turns out we didn't even need to put in electrons. They come in for free in the ablation. So we made magnetic fields and put a penning trap here, and this is the initial setup, and we got the first penning trap in Brazil, actually. Hopefully there'll be another one here in São Carlos. We are gonna be collaborating in a project, hopefully soon. And the future of this is in Rio, we're gonna try to make a chip, an atom chip, using a penning trap with calcium plus to do clocks and to do quantum computation as well. I think Brazil has to develop, even though we are far behind, even though we are not competitive, we have to develop some infrastructure and train young people and send them to the best places around the world so that they can come back and Brazil be able to eventually make its own hardware on quantum computation. Otherwise, the other countries will close themselves up and will not have a chance of doing our quantum computation if it works, okay? So I think we have to do that. And this is inspired by a group in ETH in Zurich who just did this penning trap, and they also just started a company. And of course, you know, companies in quantum bits are everywhere now. People are doing a really nice job. Rainer Blatt in Austria, people in the US, people with Rydberg atoms, with ions, with besides the Joseph Junction systems, right, the solid state systems. But we don't know which platform will be good. And just to mention, we are also in a side project, an applied project. We are making an optical gravimeter using the high precision laser measurements that we know how to do. It's simply a Fabry-Perot, okay? And we can get actually quite a nice resolution. Just last Saturday, we measured 30 microgal in a few seconds. So we should soon be able to see the tides and things like that in a very robust and compact system, okay? So the perspectives in alpha, we did this 1s2s spectrum, parts intended 10 to the 12. Now we're gonna publish in under parts intended 13. We don't know if it fits the hydrogen line or not yet. It's blinded. You'll soon find out. Actually, we don't know. We'll find out soon when we do the unblinding. And the nice thing about this transition is that it checks physics. It checks electromagnetism, it checks QED, and it even goes into QCD. Once QCD, quantum chromodynamics, start predicting the nucleus, the proton, okay? We've checked that the antihydrogen has zero net charge, as it should. We did laser cooling, microwave spectroscopy, hyperfine measurements, and so on. And we did the first gravitational fall. But we want to do a much higher precision. That's why we're importing people like Guilherme Tino and Roger Miller, right? And the question is, will CPT hold? Will the frequency of antihydrogen be the same as hydrogen? Nature knows. We'll be keeping on asking. pushing the precision, we want to go to beyond parts in 10 to the 15, okay? And see what happens. And will the weak equivalence principle also hold? It says that everything will fall under the same acceleration under gravity, independent of its composition. That's Einstein, okay? So we'll see. And in Rio, we've created this technique, which is a nice source of atoms, molecules, and ions. So we'll soon be doing hydrogen spectroscopy there because we have a colder source than Ted Hench has. So in principle, once we build all the metrology and so on, we would be able to do a higher precision in hydrogen than is done presently. And there are other things we're doing, penning traps and so on. So this is my new lab in Rio. If you come to Rio, please come visit us. Finally, after 30 years being at UFRJ, promised the lab for next year. Finally, we got the new lab. It looks nice. And I just want to say saudade to Kleppner and B. So many inspirations, so many stories, so many things. Thank you so much.
Thank you, Claudio, for the amazing talk. Do we have questions from the audience? Yes.
So, thanks for a nice presentation. I wonder how long you take for producing these and how long you have to study them after you trap. For example, how is your dirty cycle of your experiment?
Yeah, so right now, it takes us a whole day, around 24 hours. We start one day to, so the CERN sends us antiprotons every few minutes. We capture them, cool them, and then transfer to the trap where we mix with the positrons, okay? And we keep on doing that, and we can accumulate these cycles. And then we start doing laser cooling. And it takes us a full day to reach what we are now calling a megastack. Because when we started, we had one every 20 minutes, one signal, okay? In the very beginning. Now, we produce over 1,000, okay, after this full day at low temperatures. So low temperatures meaning around 7 to 10 millikelvin after laser cooling, okay? And, I'm sorry? Well, it depends. I mean, the penning trap, the capture of the antiprotons, that's 50 million Kelvin, okay? After we electron cool and so on, so they come to this the penning trap where we mix. We only keep atoms that have energy below 500 millikelvin, so half a Kelvin. After they are in this trap, which the average energy is about 300 millikelvin, then we laser cool. Takes a full day, this process. And then with this laser cooling, we get down to between 7 to 10 millikelvin. No, we start with, the antiprotons start at 50 million. Yes. Of course, CERN generates them at, no, but already in our experiment, huh? When we first trap them in the penning trap, it's a 3 kilovolts, so it's a 30 million. 30 million, yeah, sure. Penning traps are easy. So, okay, look, it's 3 kilovolts, 3 times 10 to the 3. 1 electron volt is 10,000, it's 10 to the 4. So you're talking about 3 times 10 to the 7 Kelvin. Yeah, it's a penning trap. So penning trap are easy.
Claudio, just a very nice collection of work in there. Now, I was just thinking here, what will be the most interesting thing to do with antimatter? I was always thinking that reactivity and things like this to try to understand some more fundamental stuff on. When they are together, if they destroy all or something survive, for us to understand some cosmology or something. But you seems to be going a lot onto the precision spectroscopy. So what you think is the most interesting thing to do here?
Yeah, so this has been a debate in our experiment for many years, because some people come and say, look, we can do a quick measurement and measure cross-section with different materials with anti-hydrogen, right? Right? And then we say, look, we set up this experiment for a very fundamental physics goal. If we start going after the low-hanging fruits, right, after the easy things, but not so fundamental, we get diverted from our way. I think now that we are able to produce this code sample, we have an obligation to society. I mean, this is a 30 years experiment. A lot of money invested. A lot of people gave their lives in this experiment. So we have the obligation to do the best we can in the most interesting direction. And so far, what we think is the most interesting direction is these fundamental measurements. So measuring the antiproton size, measuring the transition and the comparison between matter and antimatter to a very high precision, measuring gravitational acceleration, because maybe there is a different coupling somewhere for gravity that gives you a difference. Of course, it would never appear in the first experiment. The first experiment was just built to say whether it fell up or down, okay? And indeed, that's what it did, okay? But now we want to measure this at higher precision. There are people proposing to make H2, H-bar 2, so anti-hydrogen molecules. That's possible. And there are transitions in H2 that you can access even higher resolutions than in H. It's a possibility, okay? But, I mean, this is the kind of fundamental physics that we can do. It's very hard to produce these things, so it's not very useful for other applications. Of course, you all know that positrons are used for the positron emission tomography exam, right, in medicine. Some guys that were with us in Athena, they did a whole set of experiments with using antiprotons for therapy, for cancer therapy, because the antiprotons can come in, deposit their kinetic energy in a very small, in the Bragg peak, in a very small region, and not only deposit their kinetic energy, they annihilate. So their destructive power of the cancerous cells would be tremendous, right? And their results were positive, but it didn't justify to start a new therapy based on antiprotons. But there are always questions about this, right? This possibility. So I don't know, Vanderlei. I don't have a good answer. If you have a suggestion, please give me. Yes?
Hi, Professor. Thank you for your presentation. And I was wondering here, just out of curiosity, what would be the next long-term step regarding the creation of antimatter? Would it be to try to create anti-helium, anti-lithium? Is it too unpractical? Is it too unreasonable? Is it useless? What would be the next step?
Yeah, that's a very good question. A lot of people ask that, and I think we should hire, instead of Tino and Holger Miller, we should hire Dan Brown. You've read the book, Angels and Demons, no? So in Dan Brown's book, he is a fictionist. He writes about a method that they find that can produce huge amount of antimatter by some resonance something. And then he makes a bomb of antimatter to blow the Vatican. So that's the plot. It's a very nice book. And so the problem of going to the other elements in the periodic table, in Brookhaven, they have produced and they measured, they have produced the antiprotons and the antineutrons, and they have produced antideuteron, which is the nucleus of the deuterium atom. So it's an antiproton together with an antineutron, right? It turns out that the production of antideuteron is already 1 part in 10 to the 3. So it's 1,000, 1 over 1,000 of the production of antiprotons. So if you think that now our experiment takes a full day to produce 1,000 atoms, or a little more than 1,000, right? If we were to make antideuterium, at this stage we are now, we would take a full day to produce 1 antideuterium atom, okay? But it's possible, sure it's possible. If we find some sort of resonance or some energy regime where the production of anti-helium, anti-alpha, the nucleus of helium, is much more efficient, then it would not be out of question. But so far, people, I don't know if people haven't looked or whether it's just becomes harder and harder. Of course, you need higher energy beams, but that CERN has, right? There's no issue with energy. I think the best application I can think of antimatter counterparts, right? I think this is the best application. Because unless you find a way of producing huge amounts, if you find a way of producing huge amounts, NASA was interested from the beginning on anti-hydrogen, on antimatter, because you could invest a lot of energy to produce a lot of it and take it into a spaceship to go to Mars in a going and coming back trip, right? Instead of just, you guys remember the guy who advertised a trip that was just one way and people signed for that, right? They wanted to go just one, because the fuel, we don't have fuel enough to take people to Mars and come back, okay? So people were willing to go just one way, okay? Now, if you want the most powerful chemical fuel that you, or physical fuel that you could find, would be antimatter. So if you want, I mean, that's an application, because then, but it takes you a lot of energy to produce it, right? And then you put it in a magnetic bottle. Actually, one of our colleagues, like Stefan Ullmann from the other collaboration, is transporting antiproton inside CERN. He wants to bring from CERN to Germany, where he has a new lab there, okay? But he does measurements of a single antiproton at a time, okay? So that's a different story. But that would be one application, energy, but only not for the Earth, because you spend much more energy to create than you get out of it, right? But to go to space, that would be justifiable.
I wonder, I wonder what your friend does at the border. I have a suitcase of antiprotons.
Yeah, that's the most difficult part is for him. That's why he only did inside CERN. Because if he tries to go to Germany, can you imagine he goes in the border and the guy asks, what do you have in there? Oh, it's just antimatter. Okay, here. Puts you in jail immediately, right?
No, I just want to clarify. When the student spoke about applications, it's not making some product or some device that can. Is once you have the antimatter, kind of measurements you can do to apply, to understand. Application does not mean only, right. You know, application means advancing fundamental knowledge too. And not long ago, Claudio, I saw a talk about producing nuclei of antiprotons together with neutrons and study the decay. It seems that there are a lot of fundamental things there. So, of course, I mean, it seems, at least the way the guy put, is much more interesting than produce the antimatter neutral. It's producing the nuclei and study alpha decay and beta emission and things like this. Because then, electron will not, beta will be the opposite, will be a positron, right? So.
Right. Yeah, no, I mean, nuclear physics has a lot to develop, right? I mean, they have done amazing jobs in understanding a lot of nucleus, but yes, so study nuclear physics would be a great development. With these measurements in hydrogen, if QCD can, it's called lattice QCD, where they calculate the proton, if they can produce, the structure of the proton to a measurable thing, then we will already be probing this theory. And then you would go to more complex nuclei, right, to make sure that you understand the theory correctly, right? So this is very interesting. But we are not at that stage from the theory point of view yet.
Good. I think it's a good point to stop. So, Claudio, thank you a lot again. Let's thank Claudio.
Thank you for the opportunity.
And lunchtime, we'll be back around 2.